Hello, I'm going to demonstrate free fall. With free fall, we have an object falling in the Earth's gravitational field. Under the influence of gravity, the acceleration is constant, independent of the mass of the object. So the velocity changes at a constant rate of 32 feet per second, or 9.8 meters per second, independent of the mass of the object. To demonstrate that, I'm going to climb up on this table and drop a number of objects. Being careful, of course, to not drop myself, because I would fall at that same rate. Here I have two masses. The large one is 1,000 grams. The small one is 10 grams. So the large one is 100 times the mass of the small one. And as I drop them, you want to watch and see that they fall together with the same acceleration. Their velocities will increase at the same rate. If I start them at the same time, they should strike the floor at the same time, falling with a constant acceleration, each the same as the other, 32 feet per second, or 9.8 meters per second. Here we go. So we see that indeed they do fall at a constant rate of 32 feet per second, independent of the mass of the object. Now, if I have an object here, in this case a meter stick, that's pretty much where the mass is uniformly distributed along the length of the stick, then we would expect all parts of the stick to fall at the same rate. This 10 centimeter section and this 10 centimeter section, each of these sections would fall at the same rate as each other section, and each part of the stick, in fact each atom and molecule, will fall at a rate equal to the acceleration due to gravity of 32 feet per second. Now that's true whether I drop it in a horizontal position or whether I hold it on an angle. If I let it fall on this angle here, it might be a little more dramatic. You can see that it doesn't matter what the orientation is. Again, we're neglecting air resistance, talking about free fall. So as I drop this stick, releasing both ends of it at the same time, it should fall, and that orientation should be maintained. And we see that that is indeed the case. Now, if I have an object that's heavy on one end and light on the other end, that same principle would apply. Let's see about where the center of gravity of this is, somewhere near the head of the handle. If I were to poke a hole right through there, I could put a rod there and balance it at about that point. So we see that this end of the hammer is definitely heavier than the handle end. So if I were to hold it like this and drop it and talk about Aristotle's reasoning of heavy objects falling faster than light objects, we would conclude that the heavy object should fall faster, the heavy end should fall faster. But in fact, the acceleration due to gravity is independent of mass. All parts fall at the same rate, and we'll see that the hammer will maintain its level orientation if it starts out that way as it drops and lands on that pillow. As I drop the hammer, releasing both ends at the same time, the hammer will fall in that same position all the way down, indicating that the acceleration due to gravity is independent of the mass or the shape of the object falling, neglecting air resistance. Now, here I have a pop can. It has water in it, and if I pour a little bit of water out of that, we'll see that each particle of water falls at that same rate, 32 feet per second. Now, if I were to poke a hole in the can and the water were to flow out, what would happen to the water? Each particle of water would fall at that same rate, and we'll see how that works. I'll take my pocket knife here, poke a hole in the can, but before I do the experiment, I'll ask the question, what would happen if I drop the can while the water is flowing out? Well, if you think about it, the can and the water would then fall at the same rate, so at that point the water would stop pouring out of the can. And so as I drop this, you'll see as soon as it leaves my hand, the water will almost immediately stop flowing out of the can, and the can and the water will fall at the same rate with the water now contained inside the can until it hits the bucket at the bottom. So, can is almost full of water. Poke a hole in it, let the water come out, drop the can, and the water stops flowing out of the can as the can begins to fall. Free fall motion.